Google Maps looks at a map with millions of roads and hands you the fastest route in a fraction of a second. And notice, it's not the route with the fewest roads. A long, empty highway can beat a short street stuck in traffic. So how does it find the fastest when every road takes a different amount of time? The engine behind it is Dijkstra's algorithm, invented in 1956 and still running inside your phone and the entire internet. It's a guaranteed interview question, and once you see how it spreads across the map, it's genuinely beautiful. This is Logic Lab, where computer science becomes something you can see. Today, how to find the shortest path when every step has a different cost. Last time breadth first search treated every edge as equal, it counts hops. But real graphs have weights. Roads have minutes, networks have delays, flights have dollars. The edges are not the same size. So shortest now means the least total weight, not the fewest hops. The 3-road route adding up to 10 minutes beats the 1-road route that takes 30. Counting edges isn't enough anymore. We have to add up the cost. Here's Dijkstra's beautifully simple idea. Always expand the node you can currently reach most cheaply. Lock that one in, look at its neighbors, and repeat, always growing from the cheapest known frontier outward. To do that, we keep a tentative distance to every node, our best guess so far of the cost to reach it. The start node is 0, naturally. Every other node begins at infinity because we haven't found any way there yet. Now the loop. Pick the unvisited node with the smallest tentative distance and settle it, declare its distance final. Because we always pick the cheapest, no later path can beat it. That's the key insight that makes the greedy choice correct. Then relax its neighbors. For each one, check. Is reaching it through this node cheaper than its current best guess? If so, update that neighbor's tentative distance. Then go back, pick the next cheapest unsettled node, and do it again. Watch the settled region spread outward from the start like ripples on a pond, always claiming the nearest unclaimed node next, until the destination itself gets settled. At that moment, we have the guaranteed cheapest route, and we can trace it back. The one expensive step is repeatedly finding the smallest tentative distance. Do that with a priority queue, a min heap, which always hands you the cheapest node fast. That brings the whole thing down to about O of E plus V times log V. That heap is the difference between instant directions and a frozen phone. It's what lets Dijkstra sweep a continent of roads in milliseconds instead of grinding through every possibility. And it's everywhere. Turn-by-turn navigation, internet routers picking packet paths, pathfinding in games, even flight and delivery planning. Anytime you need the cheapest way through a weighted network, Dijkstra is the workhorse. 2 catches worth knowing. Dijkstra assumes no negative weight edges, for those you'd use Bellman-Ford. And if you actually know which direction your goal lies, you can stop exploring away from it and go even faster. That smarter, goal-aware version has a name. Recap. Weighted graphs need least total cost, not fewest hops. Dijkstra keeps a tentative distance to every node, repeatedly settles the cheapest unvisited one, and relaxes its neighbors, rippling outward until the goal is reached. A min heap makes it fast. About E plus V, log V, no negative edges allowed. Dijkstra explores in every direction equally, like ripples, even away from the goal. But what if it had a hunch about where the destination is and aimed for it? That smarter search is next on Logic Lab. See you there.